Professor, you're muted if you're trying to talk to us.
Okay, 7:30. Let's get started. '67, I believe, quite a good percentage of students joined today. There are a few more coming up. Why don't I just take a few minutes to have a poll for your class preparedness? 50 out of 73 response, about 58 out of 73. 67 out of 73. So 1 minute, or all of you participated. 67 of 73. 3 more seconds. 68 of 73. Okay, I think 1 minute is up. Let me enter poll and share the result. Some of them, okay, none of them is 16%. This is low, but please, all those people, please make sure you are prepared for today's topic and you have questions so that you understand the discussion and everything goes on in the class. And similar percentage, a little lower, is not reviewed the lecture topics, the notes. So make sure you do that. Couple of you have a question. I haven't checked the discussion board lately, and I still owe you one explanation about the asynchronous reset preset, how it works. I didn't have time to get back to you on that part. So yeah, I'll try maybe next class, maybe I'll try to do that. Let's see. Or if not, maybe after the midterm, I'll start explain. That's not important for the midterm, that asynchronous reset preset. Okay. Any question? Or should I just check the discussion board? Why don't I do that as well? Before we start, like on the theories, just to let you know, there is one discussion topic I have made it up for the midterm review topics, and I have added to your to-do. This is nothing graded or anything. This just to remind you to review that discussion. It has all the descriptions of the upcoming exam and so on and so forth. And we'll have one day of midterm review day, which I believe is when yours is 14, right? October 14 is your October 12 that we'll discuss for the review for the midterm. Okay, so that's one thing. And what else? So let's see. So I hope you guys all have started to do the project 2, and project 2 conceptually is related to this lecture 11 as a whole. And there is one video which I marked optional, which is like microcode generation from the controller unit, or from the controller unit. That video will help you to kind of make your conception clear for the project 2, what needs to be done. Though directly that specific video is related to your project 3. In project 3, we will deal with the microcode generation and we'll try to use them. But in project 2, it's a similar concept. Though it's not the microcode, but it's more like an control signals going out of the control unit to different part of the processor, so and the computing system. Let me, why don't I just try to explain in a very nutshell on a top level view of what needs to be done in terms of modeling the processor at the behavior level. Okay, so I hope you can all access my screen. Okay. All right, so so if you explore all the files given to you in the project 2, you will see we have the very similar system as we were discussing in lecture 1 and 2, those general organization of the processor and so on and so forth. So there is one specific code for the microprocessor itself, which you don't need to touch. And there is a code for the memory, which is also you don't need to touch. This is already given to you. And memory has this address port, a bidirectional data port, and read write control signal. And there is a clock, like, yeah, I'm not going to like mark the clock because it is everywhere in this design. It's a synchronous design, so I'm omitting this clock, reset, preset, all these things are there. Assume that. I'm just trying to highlight the main things here. On the processor side, there is an output port. I mean, the Verilog file, like this is like, I think processor.v. And this is, I think, the memory.v implemented. And on the processor.v, you can see this address is a 32-bit bus going out. There is an in-out data bus, which is again 32-bit, an outgoing read signal, outgoing write signal from the processor. Okay. And there is, inside this processor.v, you will be seeing there is the instantiation of the registers. Register file, which you are going to implement. There is an instantiation of the ALU, which you are going to implement. And there is this control unit, instantiation of that you are going to implement. From the control unit, you see that at the output side of the control unit, there is an address for the memory address, which basically goes here, okay? And also there is this control like memory read, memory write, these controls all connected here. And also there is like on the register file side, if you have already implemented, you know that there is this read and write signal there. And from controller, there is a register read, register write signal. And they are all connected through here. So if you look at that processor.v file, you will see all the connections are made there for you. You don't need to touch it. But conceptually, it is this, like these are the control signals. Okay, so this is one control signal, another control signal. This is another control signal, this is another control signal. And definitely the addresses and all these stuffs are issued by the control unit. There is an address associated in the register file itself, like read R1 address, read R2 address, and so on and so forth. So all this read address 1, read address 2, etc., those are all coming from the controller. So controller is the main unit, which is actually at different point of time issuing this signal to the other component to make sure all these things are in function together as a complete processor. Conceptually, any questions on right till now? Okay, so on the controller side, that means, now let's look at the controller side. Let's first talk about the interaction with the memory. So there is a memory address, memory read, and memory write signal, and also data from the memory. And this is like a bidirectional data, which is going all the way to the memory. So this is a 32-bit. This is also 32-bit. Okay. And also remember, this controller goes through these different stages, right? So this is like, let's say it's instruction fetch, instruction decode and register fetch, exe, mem, write back. So remember, there is a state machine you need to implement. State machine that cycles through these states, like it generates those states in a binary encoded form. So per clock cycle, your state machine goes through this state. Now, what you need to do here in the controller as a behavior description, and at this point, let me emphasize one more thing to you. When you are coding with a Verilog, don't keep the mindset that you are writing a program. You are not writing a program. You are describing a hardware. Okay, so you can program a hardware through your high-level language, but what you are writing in the Verilog, it's never a program. It is just a description of hardware. So come out of this writing program mindset and try to switch to the writing and hardware description mindset. So that will actually make your life and conception all easier than sticking to the writing a program in a Verilog, that concept. But anyway, so in the state machine wise, what you need to do is basically conceptually implement this thing. If I am in a state equals instruction fetch, what I need to do? I need to send memory read as 1, memory write as 0, and I also need to send correct address at this point. So instruction fetch, remember, like if you review this lecture 11, you'll see the instruction fetch is basically sending the memory address from the program counter. So practically this is equal to program counter. Okay, and of course there is a little trick around here. Please review the project guide, how to connect the memory bidirectional data, but it's somehow you get it from here, okay, from the memory after this cycle is done. So what happens then to the other control signal? So other control signal like memory read, memory write, etc., we want to set it to the least risky state. What I mean by that, maybe I should write the memory read as a 1-bit 1 and memory write is 1-bit 0. Why it is safe? Because if I put a register in a read mode, I'm reading the data, I'm not committing anything into the register file or the memory file, so I'm safe. Rather yet, if I have a hold condition implemented on the register, then I should actually put it in the hold condition. Let's say 0, 0 is a hold condition on the read and write signal of the registered file. So I need to make sure I put it in a hold condition. And what else? ALU is a combinational, so there is nothing control, and whatever output is coming out, unless we are writing back into the registered file, it doesn't matter. It is not harmful. So I think mostly to watch out these register file control signal and the memory control signal output out of the control unit. That's what you want to be concerned about. Then a question so far on the instruction fetch side? Okay. Now similarly, if I have something like if my state is somewhat like memory, I'm in a memory, right? Now I have choices. First of all, what is my memory address going to be? So remember, it is kind of what instruction? It is basically your, let's say, load word, register 0, register 1, 10, something like that. So practically it means that memory location from the register 1 plus offset 10, you'll write it back in the register 0. So this is your function, right? So your address calculation is coming back from the ALU. Address calculation is coming back from the ALU. So somewhat you know that ALU result is coming back onto the controller. I think there is a specific port for that. I think ALU result or something like that. Let's assume ALU res is that port. So what you do here is you know that ALU is giving you the memory, right? And then you check like if my instruction equals read, memory read, or no, I should say if my instruction is load word, then conceptually you memory read to make 1, memory write to make 0. Otherwise, if my instruction is store word, then conceptually you need to do memory read is 0, memory write is 1 for that cycle. And of course, you need to take care of the other control signal. You need to think of what are the other control signal going to be at that point. Otherwise, you just don't take any action, like put the memory in a read mode or put the memory in the hold mode if it is available. But don't take any action in the memory state unless the instruction is load word and or store word. Make sense so far? Any question? Okay, so conceptually,
I don't think we have the memory result register in the control unit file.
memory result? Or
We don't
memory-
have this one. Yeah, we have only OP1, OP2, and OPRN.
Yeah, that's for the ALU, right?
No, yeah, but like, how do we get the result from the ALU? Do we like make like another register by ourselves?
Let me open up the code for you. Just hold
Oh, I see, something like that.
control unit. Okay. Yeah, let's look at this this thing, right? It has a description of all the things coming in. So here, ALU result is as input to the controller.
Oh, okay, I see.
Yeah, just go through this signal list and what is their purpose, you'll know. So
Yeah, sure.
basically, you need to use those signals, incoming signals, to make decisions at the very different states. And here are the different output signal you need to think of at each phase and at each with respect to each of the instruction, what needs to be spit out for them. Okay, so that's the very core of the problem. So what I mean is like we have this set of output signal from the controller, and controller goes to each of these stages or cycles, right? So each cycle, let's say this is my, okay, let's say SC is my set of output slash control signal from controller. So what you need to ask yourself at each stage, what is my this controller output and control signal value would be? That is the basic problem you need to solve. You know? Like for example, like this SC for this project consists of this control wise, it is RF read, RF write, ALU operation, memory read, memory write. These are the control signal. And information wise, it is like data to be written on the register file, address where register file should be written, address from where register file should be read from R1 and R2, and then what are the operands for the ALU. Those are the information flows through this controller for this project. And this group of control signal, which is like RF read, RF write, ALU operation, memory read, memory write for this case. You can think of these are your these, if you group them together, that becomes your microcode for your program. But let's not ponder much on the microcode right now. Microcode is much bigger thing and needed for the gate level modeling. For register behavior level modeling, we can just separately treat them, this group of control signal, and set them to their correct values at each of these stages, right? So each stage you need to ask yourself, what are these control signal value going to be? So you should put the right control signal at the right moment. Make sense?
So professor,
Yes.
you mean by like each stage will produce like all like 10 or something outputs? Like for each stage you have to decide like which for every single output what will the value be, and like for each stage you have just this list of the value calculations for each of the possible outputs, and you do that for all 5 stages?
You need to consider, yes, all the control signals, okay, all these outputs, what it's going to be. For some instruction or set of instruction, you can keep it like a constant from the previous state. Like if you now, after analysis, you see some signal is not changed from IF to ID, you don't need to change it actively on the code side. But theoretically, it is there. You mean what?
So theoretically, you mean like all the outputs change, but in the code, we don't have to actually change it?
Yes. So theoretically, all this output needs to be set to some value. Now, when you are writing the code, you may see that, okay, from instruction fetch to register fetch, my ALU operation code is not changed. So you don't write that change of value. It is the same value. So you just stick it, like use it from the previous stage. You just, because these are all registers, this output will be defining as a register. So once you write that value there, it will be held there. So unless the value is changed, you don't need to rewrite them again. So that will make your code shorter. Make sense, Kevin?
Mm-hmm. Thank you.
Yeah, so, but conceptually it is all there. Like each of the stages, you need to critically think what are the output is going to change and what value. Okay, and then implement the code. All right. Now, a little bit on this, this how are we going to know? Like you see, like in my code, I have this like action depending on what the current instruction is going to be, right? So this is somewhat related to the parsing problem of the incoming data, right? So in the instruction fetch, during the instruction fetch, memory is going to send me back the instruction code for the instruction. That is the 32-bit data which encodes the instruction. And what is that port is? This is the incoming port of the, this is the IO port. RF data, sorry, not RF data. Mem read write. Where is my mem? Mem address, mem read, mem write. Oh, out. Oh, IO. Okay, mem data. So this is in out. So during the instruction fetch, this in out will act as an incoming data, and you need to act and parse and store the value for that one, right? And your project guide already actually gave you certain clue and hints how to do it. Let me pick up your project guide. Yeah, look at the example of this Verilog task. What it does, it basically, let's say this is your incoming memory data that is from at the instruction fetch you are getting from the memory. Then you are assigning different register combination to it. right? I'm defining opcode as a 6-bit, and then RSRD RT as 5-bit, shift amount is 5-bit, function code as a 6-bit, immediate field as a 16-bit, and address at 20-bit. And at this point, I really don't know if it is an R type, I type, or J type instruction. All I am trying to do is practically parse them and divide them into different parts. I'm assuming, okay, instruction. First, I'm assuming this is R type instruction. So I'm just breaking this instruction into these fields: opcode, RS, RT, RD, shift amount, and function. And now if it is an I type, then I need to break it down with the opcode, RS, RT, and immediate. And if it is a J type, I need to break it into opcode and address. So at the end of the day, I know the opcode, right? And then look at this case based on the opcode. If that field, opcode field is 00, I know it is a R type. Then I look at the function code and decide, okay, this is my add, this is my sub, this is my mald, and so on and so forth. It is, yeah, don't take it this code from here. Like, make sure you cross-check with the instruction set architecture that I have given to you, lecture 1, those slides. Make sure those code actually matches, because this has been written very long time back and probably some code has been altered. So make sure these code are up to date, okay? But point is that you are picking up on this incoming data and parsing it and storing it for later use. And likewise, you can actually use the if conditions as proposed here. So during the instruction decode and IDRF fetch, you need to make sure you execute these assignments, basically. These assignments, okay? Then you have the opcode, then you can actually have some opcode or instruction-based specific action if needed to be taken. Okay, so this lecture 11 will should give you a broad idea of what each of these phase does in terms of controlling other components. And definitely that optional video of microcode generation will help you here and as well as on project 3. So though it is optional, I strongly recommend you to basically review that. Question? Okay, how is so what's your general feeling about this lecture 11? This is the first topic that we are actually picking up for core computer architecture. Scary? Or okay? No, I don't know. Anyone wants to comment on that? No? Yes?
I'm spooked.
Was that trained?
It said, consider me spooked.
Yeah, that's true. So one can pretty much lost in terms of all those data path construction and especially the number of multiplexer usage onto the data path. But I hope, okay. I see there are chats on these. Okay, let's see. Just a little scary, a bit scary, kind of scary, seems familiar, a bit scary, quite complicated, super interesting, pretty interesting material again from the first few lecture, like the microprocessor memory drawing, and feel it lost. Yeah. So basically you need to spend a lot of time on this lecture, and that's why I allocate the whole week for you to review it. Okay, and sink in with the concept from the lecture 1 till here. You need to synchronize all your concept together now at this point. Unless you synchronize all these concept here, very clear, the next lectures is going to be way off the roof. I can guarantee you, okay? And as we go, like this is probably the last lecture where you have hands-on, like where you deal with little bit of bits and bytes and how things control exactly. You can experiment on the Verilog and make some project and so on and so forth. But after this, after the midterm, lectures are going to be pretty abstract. Like we'll go from the system to parallelization. I don't know whether we should touch the cloud or not, but somewhere in the distributed computing and all these abstraction will come in. And there is no such dealing with at the bit level, but it is more like an abstract concept. So you need to make sense of those abstract concepts. You guys need to make sure you understand these concepts. Is that a deal? Okay, so please make sure you review, re-review, and more importantly, discuss within your peer groups. This is very important that you basically go and chat with your study buddies. That's why the study groups are created. Please make sure you meet weekly, frequently to understand this topic till you know that you understand. All right, so I don't have much thing to do tonight, and I believe you have more work to do on the project 2, get it work. And as I said, project 2 is also like you can discuss among your groups and help each other in terms of debugging and shooting problems, but not really copy paste the code. That's the only condition there. Copy paste code or copy paste report, that's not permitted, but discussion is okay. Test bench sharing is okay. Test program sharing is okay. Not the code implementation. Okay, so make sure you get good use of your study group. That's very important. Okay, then we can stop tonight pretty early tonight then. And I'll leave you to study again, go back on the lecture 11, study more in light of these, make a link with the project 2 concept, make a link with the lecture 1, till the lecture 1. You need all this lecture to link together. All right, good night then, and see you on all Wednesday. And I hope to have more questions on this part.